Maxwell Boltzmann distributions. Particles in a gas move around with random speeds and directions, but one can model the predicted distribution of speeds with a Maxwell Boltzmann distribution. Let's say you have 100 gas particles. On average, they're moving at 350 meters per second. However, if you made a bar chart showing how many of those 100 particles were moving at specific speeds, you might get something like this. 10 molecules are moving at 250 meters per second, 40 molecules at 300 meters per second, 30 at 350 meters per second, 15 at 400 meters per second, and 5 particles are moving at 450 meters per second. That adds up to 100 total molecules. We can even draw a curve of best fit, as shown to the right, something like this. If we then increase the average speed of the molecules, you'll see a shift to the right. It's the same number of molecules, just distributed differently. See how the peak was here, and now the peak has moved over to the right. Maxwell Boltzmann distributions show the probability of finding a molecule traveling at a specific velocity when a gas is at a specific temperature. On the graph to the left, you can see that the average velocity is about 500 meters per second, and the most probable velocity right here at this peak is about 390 meters per second. The area underneath this curve represents the total number of molecules in the gas. As the temperature of a gas increases, the average kinetic energy of the molecules also increases. This means that the molecular speeds are increasing. Shown below are two graphs representing the same gas with the same number of molecules, but at different temperatures. As the average molecular speed increases, you can see the graph stretching further along the x-axis this way, and the peak getting shorter. So it was up here, and now it's down here. So the peak has moved to the right and down that way. However, it is important to note that the areas underneath these two curves are equal, since the number of gas molecules has not changed. Open the Physics Aviary Maxwell Distribution Lab to see how this works in real time. Observe what happens to the shape of the graph as you change the temperature. You might also notice that changing the gas itself will change the shape of this graph down here. This is because different gases have different molecular weights. To summarize, a gas at a lower temperature will have a tall peak closer to the y-axis. That same gas with the same number of molecules at a higher temperature will have a lower peak further from the y-axis. They both have the same area underneath the curve.